Thank you, Mario, and thank you to everyone who was involved in organizing this great event. And it's really an honor for me to be here today and talk to you a little bit about some of the work we are doing across the pond in Heidelberg, Germany, on the topic of the inner protoplanetary disk. And I'm specifically going to talk about a model about the evolution of the inner disk over longer periods of time that also include phases of episodic accretion, meaning accretion outbursts onto the central star. So we're going to hear a bit more about accretion outbursts in the talks to come, and I'm going to present a type of accretion outburst that is a consequence of the structure of the inner disk. And I'm, of course, mostly interested in the consequences of the episodic accretion event on the planet formation conditions in the inner disk. So I'm going to take you on a wild ride, or fiery ride, literally, starting from somewhere in a pre-burst phase, going through the outburst stage and back towards a quiescent state, and then all the way back towards the start of the next episodic accretion event. So everything I'm going to talk about is presented in our paper from late last year, and it's based on a hydrostatic model of Mario and his colleagues from 2019. So we're working with a two-dimensional axisymmetric inner disk starting from 0.05 to several AU, which is irradiated by its central star. I'm saying here that the structure that we are seeing is analogous to the hydrostatic model because, strictly speaking, this structure here is not in a hydrostatic equilibrium or not in a steady state. And we are going to find out why in a couple of slides. But the most important feature, for us at least now, in this structure and in the model from 2019 is a pressure maximum, a pressure bump, located here between 0.1 and 0.2 AU in the inner disk. And those pressure bumps are, of course, always the things to look out for when it comes to analysis of protoplanetary disks, because they are generally capable of trapping solid material within them and providing favorable conditions for planet and planetesimal formation. But let's not get ahead of ourselves, and let's have a look at the details of this model. Most of those have already been beautifully introduced by, in the morning session today. So we are doing all these investigations in the context of radiation hydrodynamics. So we, of course, take into account the irradiation by the central star, heating up the disk material. And this radiation is transported throughout the whole domain via a radiation transport description. We prescribe the dust sublimation via a certain dust sublimation temperature, represented here by this green contour line. So in practice, this means that out here, where the disk is cool and dust can exist, the dust to gas mass ratio here has a certain maximum value of, in this case, 10 to the minus 3. And this value decreases over the dust sublimation temperature smoothly towards 0 in the inner, purely gaseous disk. There is a transition in turbulence present in our inner disk, which is represented by the MRI activation temperature, which is the black contour line here. So we say that above a certain threshold temperature, in this case 900 Kelvin, the MRI, the magnetic rotation instability, can be active and produce a lot of turbulence in the disk material. So the exact value of this threshold temperature here is not hugely important as long as it's somewhere around 1000 Kelvin. We prescribe the turbulence in our models with the typical alpha prescription, where out here in the dead zone, we have a minimum value of alpha of 10 to the minus 3, and this increases smoothly across the MRI activation temperature towards 0.1 in the inner, highly turbulent disk. Now, I'm aware, of course, that those values of alpha here are chosen to be very high, typically, but everything I'm going to talk about works at least phenomenologically the same, even if we decrease the values of alpha by orders of magnitude. And the last ingredient we need to complete this picture of the inner disk is the effect of viscous heating, so the production of heat by the turbulence in the disk. And with all these ingredients now in place, and with this picture of the inner disk painted, we can simply ask the question, is this structure that we are recovering here stable over long periods of time? And if not, what happens to the structure during or after potential phases of instability? And I mean, judging from the title of my talk, you can probably already guess that this will not remain stable over long periods of time. So we can think about a moment why this could be. So there is a turbulence transition here, meaning turbulence, for our intents and purposes, is equivalent to angular momentum transport. So in here, in the highly turbulent disk, the the angular momentum transport is very efficient, as is the accretion rate in here, in contrast to what's happening out here in the dead zone. So you can imagine if you're sitting somewhere around here, around the location of the pressure pump, you will receive a lot of angular momentum being transported outwards from the inner disk, but you cannot give it off at the same rate because the turbulence out here is a lot smaller, which means also that the accretion efficiency in here will diminish. And this means that over longer periods of time, there will be material accumulating here in this area, which leads to a buildup of density. And this buildup of density will continue, theoretically, until a steady state is reached. But the buildup of density here has two other important consequences. One is that the effect of viscous heating will become more efficient, and on the other hand, this disk area here will become more optically thick, meaning that the heat that is produced in there will get trapped more efficiently, which means that the temperature will increase here as well. And eventually, before this steady state can be reached, the temperature could reach the vicinity of the MRI activation temperature, meaning that this high density region then becomes suddenly MRI active, suddenly very turbulent and hot, and igniting the areas around it, which leads to a runaway heating effect, blowing up the whole thing. And this is what we are observing when we are letting this model run hydrodynamically for longer periods of time. And this is what we will see here in this animation that hopefully works. So in the upper panel, we have the same picture as before, the 2D temperature map with the MRI transition in black, the dust formation in green. And I also overplotted here the tau equal 1 surface, which is basically just a transition from optically thin to optically thick with respect to the stellar irradiation. And on the lower panel, there is a 2D density map, but more importantly, the surface density structure as the red dashed line. So I will let this run through twice, and I would suggest looking at the upper panel first and not the lower panel in the second round. So if we let this run, we see that the activation of the MRI inflates the MRI active region far into the disk very quickly, and then it retreats slowly back towards the star. And this is a process that's actually reflaring a few times, as we see here. But each of those reflares is weaker than the previous one, and eventually the instability sort of fizzles away, and the quiescent state of the disk, where the accretion rate onto the star is rather constant, is reinstated. So let's play this again and look at the lower panel. And what we immediately notice here is this spike in density that is pushed ahead of the expanding MRI active region and is then left behind in the inner disk. And this is happening for each of those reflares. And since each reflare is weaker than the previous one, there are multiple such density spikes placed throughout the inner disk structure. And at the end, we are left with this bumpy shape of the surface density at the end of the instability cycle. Let's have another look at this with a few representative snapshots of what we've just seen. So we're starting here in the first column with the activation of the MRI in this very small region, leading to a runaway heating effect, blowing up the MRI active region into this toroidal shape. This is what we would call the high state of the disk. There's probably a joke you can make about being in a high state, but I'm going to refrain from that. So in this MRI active region here, now the turbulence is very high, which means the angular momentum transport outwards is very efficient, and all this material that has been accumulating here is now drained onto the star very efficiently, leading to this elevation in the accretion rate. And after, also here the temperature can become high enough for the dust to begin to sublimate. And after a lot of this material has been drained onto the star, the disk can cool down again and the MRI active region retreats back towards the star. And after a few of those reflares have occurred, we are at the end left with this sawtooth-like shape of the surface density structure at the beginning of the quiescent phase. And those spikes in the density are of particular interest because each of those spikes is associated with a spike in the pressure structure. And we can have another look at the pressure bumps that are formed here in a space-time plot such as this one, where we have the radius on the x-axis and time on the y-axis, and the surface density color-coded. And the white contour lines here represent the positions of the pressure bumps. Within those 3,000 years shown here, there are two full instability cycles occurring that we've just now analyzed, one at the very beginning and one after about 2,500 years. So this is a process that is periodically reoccurring. And the reason for that is that during the quiescent phase here, we have a refilling of the inner disk by the material flowing in from the outer disk. So here we are starting with the bluest line here, which is still a bit bumpy after the initial instability. And after, over the course of this quiescent phase, the disk is refilled with material from the outer disk. What the disk aims at, so to speak, is establishing a steady state, a guess of which is represented here by the yellow dashed curve. But this steady state cannot be reached because as soon as this purplest structure is reached, then another instability cycle will be ignited and the surface density is reset to the bluest line. So let's have a closer look at one of those instability cycles. I've overplotted here the inner edge of the dead zone in blue. And as we can see, which was the black contour line before, it moves outwards and back for each of those flares and reflares. And whenever it reaches its outermost extent, there is a pressure bump placed in the inner disk. What we also notice is that there's one pressure bump here that is very stable over the quiescent phase, which is the one that was already recognized in the literature. We see that coming into the picture here. And this pressure bump is destroyed by the instability and only reinstated after the cycle has died down. And this destruction and emergence of pressure bumps, of course, beg the typical questions of how does this influence the conditions for planet and planetesimal formation in the inner disk? So are those pressure bumps that are produced here strong enough to capture enough pebbles and solid material to enable conditions for planetesimal formation? Or what happens to the material that was trapped in here already during the quiescent phase, which is then destroyed by the instability? So will it get scattered away? Will it get accreted? Will it evaporate? And those are the questions that are also already being worked on. What we, of course, have to recognize here is that those pressure bumps are fading away after some time, just due to the viscous evolution of the dead zone. But the quickness of this is just a consequence of our chosen alpha parameters in the dead zone. If we would have chosen them to be magnitudes, orders of magnitude smaller, those pressure bumps would stick around for much longer. Okay, and this leads me already to the end. So here are the two most salient points that I wanted to get across. So our inner disk structure can lead to the establishment of instability cycles that lead to accretion outbursts. And those instability cycles produce and destroy pressure bumps, which can have important impacts on the planet and planetesimal formation throughout the inner disk. Okay, and that's it from me for now. Thank you. And if you have any questions, go ahead.
So we have time for questions. I see one here.
Very, very impressive simulations. I guess I'm trying to understand or separate out the initial conditions of the simulation versus what we would expect in a disk that's slowly evolving. So it seems to me, and just correct me if I'm wrong here, that after each of these outbursts, the system is trying to relax the inner disk towards this sort of state where the density is decreasing. It's the ragged edge of the blue zone in that left-hand plot. And that if left alone, it will just stop. And on the other hand, the outer words disk is trying to charge the inner disk with more material. Yes. That's trying to force it to the dashed yellow line. So far so correct. Doesn't it mean that the outer disk has to work faster than the instability mechanism to do that charging? Because I could imagine if it was slowly trying to charge it, that this instability would keep up and then keep the disk at some steady state.
Well, the recharging here over, so the refilling of the inner disk happens over very long periods of time. So here, 2,500 years. The instability cycle itself only lasts about 50 years or so. So basically the instability itself and the recharging are pretty much disconnected from each other. The instability just produces, so to speak, the initial conditions for the refilling to work. But how fast this refilling is actually has no bearing if the instability occurs or not. The important thing is that eventually this state, the pinkest line here, is reached. How this is reached is not hugely important, or when it is reached. Just that it is reached is important for the instability to occur.
Okay, so the instability won't occur until it reaches that pink upper line.
Exactly.
Boundary. Okay, thank you.
Thanks. We'll continue here.
Okay. Hi, Adolfo Carvalho, Caltech. I really like this, but I have a couple of questions, and I can talk to you afterward for some of them. But the main one here is, do you have a prediction of the mass accretion rate over time?
Yes.
With this, and so I imagine. So correct me if I'm wrong here, but is it that you have a very large burst first, then you have a successive smaller bursts afterward?
Oh, thank you for mentioning that. I can pull up my backup slides.
Oh, nice.
So here is the accretion rate evolution. The yellow model is the one that I showed. So this is the long-term evolution with the two instability cycles at the beginning and 2,500 years later. And this is a zoom in into one of those cycles. So as you said, there is a large increase as the burst begins, about 2 orders of magnitude. And this is then like bouncing around, so to speak, for each of those reef layers until it then settles back towards the quiescent rate.
Okay, and so there's a couple of systems where we have data for the last few decades that show, like the EX loop especially, but a couple of others.
Yeah.
Have you compared with those to see how their outbursts reflect or not your?
Yes, so there's one system that I was specifically interested in. I forgot what the name was. It was Gaia 19, I forgot. But that one showed like a sort of bumpy decay of the accretion phase, which is reminiscent of this one. But other than that, so we haven't gotten very far with comparing the models to the observations yet, because the models that I'm showing here are not the final word spoken. So these models are just to show how this instability mechanism works. But there is a lot more we have to do in order to be able to compare them effectively with the observations. Like, for example, enhancing the opacity description, enhancing the alpha description, the turbulence in the disk, and only then we take the step to comparing them more directly.
Thank you.
Can we go to the left?
So I think that your initial state assumed kind of like a bright star, A star, something like that. But if you had a lower mass star, those accretion rates would be a big burst in luminosity.
Yes.
And so I wonder whether, in terms of the question that Eric asked, kind of like, what is this, is this initial condition, plausible or something? Couldn't you get the same effect even if you had kind of like a steady state disk, but if for some reason you had a big outburst of accretion, that could be a triggering time that would not necessarily have to start at time equals 0, right? Have you thought about that?
So could you rephrase?
All right, I'm sorry. I'm wondering about whether you could get the same effect from luminosity bursts.
From
the accretion burst.
Mm-hmm. So the accretion burst itself, the one that we are seeing here, has so enhances the accretion luminosity, which then can have a back effect onto the disk evolution itself.
It's not in here.
It's not in this model, but I have other models where I included that. But the effect of it is not hugely impactful on the models that I'm showing here. This is why I'm not showing it. I have not included them here.
Okay, only one final question, then we have to move on.
Okay, Jack Lissauer, NASA Ames. You're showing a process that gives irregular structure in the inner disk in a very active time, and this is going to be in a hot region, that there's not going to be a lot of planet formation, planetesimal formation, whatever. Can you think of any process or set of parameters that would bring it out to greater distances where it could have greater effects on planet
great. Yes. So, for example, if we used a star that has intrinsically a higher luminosity, then all of this would be shifted further outwards. So the dust sublimation and right afterwards the MRI transition. The question is just out there, will it be enough? Will for example, the triggering mechanism, which in this case would be the viscous heating, would that be enough to ignite the instability? For example, if we assume a Herbig star, which is very luminous, and the inner region is shifted further outwards, then this triggering would probably not work. So we need to be closer to the star in order for it to trigger.
Okay, let's thank Michael again. Thank you.